From Diamond Light Source, this is the Diamond Podcast.
Hello and welcome to episode 1 of the Diamond Light Source podcast, where we take a look at the latest science from the Diamond Synchrotron. In this first edition of the show, I'll be taking a look inside this National Science Institute to find out how it works.
An electron is accelerated to close to the speed of light and then forced to go round a bend by passing through a magnetic field. The electron, as it goes round the bend, gives out light.
Trevor Raymond, who'll be explaining more about what Diamond is and how it works. Plus, we'll be catching up with some of the key research which took place over the past year, including how Diamond has revealed the real chemical composition of a comet.
One of the things we're finding are iron oxides and chromium oxides. Now that's unusual. It's not the sort of thing we expect to find in a comet.
So, watch this space for more on the cosmic soup that spawned our solar system. We'll also be finding out how chemists are worming their way into nature's good books.
We could take these super metal munching earthworms and take them from contaminated sites, put them into other contaminated sites which don't have earthworms, and help the earthworms develop the soil and stimulate soil production and make the ecosystem healthier.
How are earthworms capable of doing this? Mark Hodson will reveal all, as he explains how these earthworms seem to survive where no other organism dares go. I'm Meera Senthilingam, and this is the Diamond Podcast.
The Diamond Podcast. For more information, look us up online at diamond.ac.uk/podcast.
Before we take a look at the science happening here at Diamond Light Source, let's find out a bit more about how it works and what it does. Located in South Oxfordshire, the synchrotron opened in January 2007. It covers an area the size of 5 football pitches and took 4 years to build. At its heart is a powerful particle accelerator, whizzing electrons at high speed around a large racetrack-style ring. As they circulate through this ring, the electrons pass through specially designed magnets which make them produce intense beams of X-rays, ultraviolet and infrared light. Here's Diamond's Director of Physical Science, Trevor Raymond, telling us how they produce this very special light.
An electron is accelerated to close to the speed of light and then forced to go round a bend by passing through a magnetic field. The electron, as it goes round the bend, gives out light.
And so knowing this, how does a synchrotron like Diamond work?
Well, what we do is we take electrons and we make them go round in a circle. We do that because it takes energy to get them up to a very high speed, and then once you've done that, you want to keep them going round at a constant speed for as long as possible. Now, the way that we do that is in 3 stages. We start, first of all, by making electrons, and then, having done that, we accelerate them along a straight accelerator until they get to a high speed, but not high enough speed to join the electrons going around the ring. And so we put them into what we call a booster, which boosts them up until their energy is the same as the electrons that are circulating around the ring. And when they're at the same energy, we let them into the ring, and they join their friends going round.
Whereabouts in the synchrotron are we now?
Well, right now we're sitting overlooking the experimental hall, which, when you look at it, mostly what you see is a lot of pipework. But if we were to look, as a bird might, looking down on the ring, what we would see would be a 24-sided polygon, 24 straight sides and corners. Now that's important because electrons go in a straight line if you just leave them to their own devices. And it's only when you turn them round a corner that actually they give out light. So we've got a 24-sided polygon, and at each of the corners we have a magnet which deflects them along the next side of the polygon.
And how large is this 24-sided coin?
Well, if you were to walk all the way around, it's 561 metres. I think that's right. In practical terms, it takes you more than 15 minutes to walk around the experimental hall. So it is quite large.
Okay, so within this large coin, you just have these electrons going at very high speeds. But now what do you actually do with this to then use in research?
If you know that light emerges every time an electron goes round a bend or follows a curve, then the simplest way to improve or increase the intensity is simply to make the electron go through a whole series of sequential bends. You make it wiggle as it goes along its path. And so if you have 10 wiggles or 10 magnets, then what will happen is you'll end up with 10 times the intensity. We call those wigglers, and those are used at Diamond.
And so these insertion devices essentially help determine which types of radiation are being created, and these spaces where they happen are called beamlines.
Yes, that's right. The insertion device create the radiation, which then streams off tangentially from the storage ring, and then it goes into a special shielded hutch-led room where we select out the radiation that we need. After that, it then will impinge upon our samples, and we do whatever experiments we have to do.
So how many different beamlines do you have here?
Well, at the moment there are 12, and these produce very different types of radiation. If I give you some examples, at the most gentle end, we have a beamline that isn't quite ready, that produces infrared radiation, and one which was commissioned just a few days ago produces ultraviolet radiation. And then there are instruments which will produce X-ray radiation that will penetrate through centimetres of matter. These are used with a very wide range of different applications, from studying the conditions at the centre of the Earth through to looking at the composition of paint, say, in pictures.
So you have all these beamlines and different types of radiation set up. What sort of scientists are using these?
A very wide variety of sciences, in a nutshell, but let me give you a few examples. If I start with areas of biology, then there are scientists who are trying to understand disease at a molecular level. These are followed by scientists who are attempting to develop new drugs, and we have collaborations with industry. But going on from that, the range then goes into the physical sciences. There are people trying to invent materials that might improve, for example, your iPod. There are others who are working on archaeology, trying to understand where various bits of pottery come from. We've even had people looking at components of meteorites.
Trevor Raymond. He's Diamond's Director of Physical Sciences. And speaking of meteorites and other objects out in space, here's Leicester University's John Bridges.
I've been using the Diamond synchrotron to analyse samples of Comet Wild 2 to find out what it's made of and how comets formed.
And what is Comet Wild 2?
It's a comet which formed beyond Neptune in the Kuiper belt, but which was disturbed by Jupiter, by a close interaction with Jupiter, and brought it into the inner solar system. And in 2004, a space mission called Stardust was able to go in front of it through its coma and sample samples of dust, then bring it back to Earth so we can find out what the comet is made of uniquely.
And why did you want to find out what this particular comet was made of?
Well, comets are the most primitive objects in our solar system. They haven't undergone all the plate tectonics, the erosion, all the different types of alteration that the rocks on Earth have undergone. So when we're looking at comets, we're understanding what processes were occurring in the early solar system.
And how did you go about analysing this comet?
Well, we took slices of an aerogel collector from the Stardust craft. That's a very low-density silica gel. We took those wafers with these tiny grains of the comet, a millionth to a thousandth of a millionth of a millimetre across, and we took those to Diamond, and we used their very bright X-ray source. When we focus an X-ray source like that onto our grains, then we can get fluorescence, or the emission of characteristic X-rays from the actual grains, and those packets of energy, those X-rays, tell us what the grain is actually made of.
So what were the grains made of?
One of the things we're finding are iron oxides and chromium oxides. Now, chromium oxide, a mineral called chromite, is a high-temperature mineral. It forms at very many hundreds of degrees centigrade. Now, that's unusual. It's not the sort of thing we expect to find in a comet, and you have a sort of traditional view of a comet as a dusty ice ball. So what on earth is this high-temperature mineral doing in there? And we've been finding other minerals like that. So that's telling us this traditional view of the comet. Maybe that's not true.
So it was previously thought that comets just didn't contain any kind of minerals or compounds like that?
Yes, it's unexpected. We're expecting to find almost invariably low-temperature minerals and remnants of ices which formed in the outer cold part of the solar system. But it looks like some of the material has actually been brought in from the inner parts of the solar system. It looks like it's been a great mixing, a grand mixing has been going on in the solar system, or went on in the solar system in the early part of the solar system's history.
So to add to this evidence, what other materials did you find in the comet?
Well, we also found, diametrically opposed, if you like, to the chromium oxide, we found iron oxides, like minerals called magnetite and hematite. Now, these are, if you like, at the other end of the spectrum of temperature, and that these probably formed at relatively low temperature, which is okay for comets, but probably from trickles of water. So it looks like, at least just very occasionally in small amounts, there may have been trickles of water on the nucleus of Comet Phil 2. So again, that's not quite what we were expecting. So there's been more going on in this comet, a more complex system than we were expecting.
But what else is this trickle of water theory then adding to your thoughts of how comets were made?
I think it's telling us that not all comets are the same. Phil 2 is a Jupiter family comet which formed in the Kuiper belt. There are other comets which form in the Oort belt, which is way beyond the extremes, outer margins of the solar system. So not all comets are the same. Ones like Comet Phil 2 seem to have sampled materials from the inner solar system as well as the outer solar system.
So now that you know this and there's been a variety of mixing when it comes to making these comets, what else will you be looking into? What else would you like to find out?
I think we need to find out accurately the bulk composition of the comet. So we can do that at Diamond as well. For instance, we have these whole cometary tracks, and we want to find out what their bulk composition is. In other words, what the percentage of iron, of silicon, of all the other elements, what they are. And then we can take that composition inventory, if you like, compare it to our meteorites, and we can see, put it in context. How does the composition of Comet Phil 2 compare to that of planets and primitive meteorites? And then we've got a better idea about the compositions of the solar system in the building blocks of the solar system.
John Bridges, explaining how Diamond is helping to shed some light on the chemical composition of the cosmos. He's based at Leicester University's Space Research Centre.
Did you know that the electrons at Diamond are moving so fast that they could travel around the world 7.5 times every second? That's close to the speed of light.
Now, we've heard how Diamond is helping scientists to learn more about the composition of comets. But now we're heading more down to Earth, quite literally, as we venture down beneath the soil surface and into the world of the earthworm. These creatures appear to be able to thrive even in land so contaminated that little else will grow there, suggesting that they may be able to help us clean up contaminated environments. Here's Mark Hodson from the University of Reading.
Well, the mystery about these earthworms is why are they actually there in the first place? You go to these sites and they're former mining sites left over from the 19th century. Metal levels are really high. And to all intents and purposes, these are contaminated sites. Plants have trouble growing there. But when you dig in the soil, what you find is earthworms. So the big question is, why are they there? How can they cope with all those metals?
And why are they there? How are they able to cope with the environment?
Sometimes it looks like the earthworms have actually evolved. They've been driven by the concentration of the metals to evolve, so they've got special methods of dealing with those metal contaminants. And we're still working on that, but there are a variety of mechanisms that they can use to actually cope with those metals. And that's some of the research we're involved in, using the synchrotron at Diamond, can actually tell us what form the metals are in, both in the soil and after they've been ingested by the earthworms. So the earthworms take the metals in and they change the form of the metal to make the metals less toxic to them.
Which metals are we talking about here?
It varies from site to site. The main sites we're working at the moment is a former lead mining site in Wales, so the contaminant there is lead. We've also got an interest in a site down in the southwest where there's lots of arsenic and copper. And also the final site we're working on is up in the Pennine ore field, and again it's lead and zinc primarily.
And what's going on then inside the earthworm to help them make this less toxic?
Well, that's the $6 million question, really, what we're really looking to find out. What it looks like in some situations and some circumstances is that the ingestion of these metals, taking the metals into the earthworms, triggers the production of a special protein which essentially wraps around the metal and makes that metal non-toxic to the earthworm. So that's one mechanism that seems to be going on, particularly for the arsenic. And that works for copper as well. For some of the earthworms from the lead-contaminated site, what it seems to look like is that, again, there's just more of a different type of protein, and in this case it's a protein which is normally used for moving calcium around in your body. But lead's very similar to calcium. It has a similar sort of size when it's an ion, and it has a similar charge as well. It's a 2+ cation. And it looks like in those earthworms that can live in lead-contaminated sites, they're just very good at producing more of this protein, modifying it slightly so that it can deal with all the lead and immobilise the lead.
So you know this about these earthworms now, and they're able to live in these harsh environments, but do they have any applications or uses?
There are a couple of possibilities out there. One is that we could take these super metal-munching earthworms and take them from contaminated sites, put them into other contaminated sites which don't have earthworms, and help the earthworms develop the soil and stimulate soil production and make the ecosystem healthier. So that's one possibility. Another possibility is to take the earthworms to contaminated sites, and the earthworms actually seem to change the form of the metal in the soil once they process the soil, and that might make the metals more extractable by plants. So we could grow plants on those sites, and with the help of the earthworms, the plants will be able to pull the metals out of the site and help to remediate the site that way.
How would they help plants be able to uptake these minerals?
It's a question we can't fully answer yet, but we have done experiments where we've grown plants in contaminated soil with and without earthworms. And when the earthworms are present, the plants are able to pull out more metals. Now, precisely why that is, we don't know yet. We've started doing some experiments, and essentially we go and collect earthworm poo and see whether the form of the metal in that poo is different from the bulk soil. At the moment, it's too early to say how the differences affect the ability of the plant to take the metals out, but it's certain that the plants are able to take more metals out. Once we can answer that scientific question, we can start to apply it in real life to real contaminated sites.
Now, you say these earthworms are only in some contaminated areas, so how do you think they've ended up only in certain areas and not other contaminated soils?
Sometimes it could just be that at a contaminated site it was so disturbed that whilst that site was being used by industry, it just became impossible for organisms to live there. And earthworms migrate very slowly. They move, on average, it's something like 10 metres a year they might encroach into areas where they're not present. So some of these sites might be so big that earthworms just haven't got there yet. They haven't had time to spread into those areas.
And so what are the benefits of using these and, helping remediate these contaminated areas?
Okay, there are two advantages to using earthworms to remediate contaminated sites. One, of course, is just it's good to remediate contaminated sites. We can use former industrial land, former brownfield sites for building purposes or for building parks, that sort of thing, rather than building on greenfield sites. The actual advantage of using earthworms or plants to remediate sites is a lot less environmentally impacting and far more environmentally sustainable than simply digging up that soil and moving it somewhere else, which is a sort of classic remedial treatment at the moment. It's called dig and dump. And that works very well, but it's not sustainable. So using earthworms and plants is a more sustainable, greener option. The key thing is that synchrotron allows us to actually burrow down into the detail and find out what form those metals are in both the soil and the earthworms. So, for example, in one of our sites, we can say that in the soil, the copper atoms, the contaminant, are surrounded by oxygens. But once we use a synchrotron, we can see that in the earthworm, that copper is modified and it becomes surrounded by sulfurs. And most probably that sulfur is related to a protein surrounding the copper and rendering it immobile.
And so what are you hoping to find out now with your research? Where are you hoping to take it?
What we're really hoping to do now is to use Diamond to answer these fundamental questions, look at the metal speciation, the form of the metal in the earthworms and in the soil after it's been processed by the earthworms. Once we understand fully how these metals have changed their form and the impact that earthworms have on metals, we'll be able to realise some of these ideas about using earthworms to remediate contaminated soils and help the earthworms to help us to remediate the contaminated soils.
So earthworms could be the answer to cleaning up contaminated sites. That was Mark Hodson from the University of Reading. That's it for this edition of the Diamond Podcast, but do join us again in April when we'll be back with more of the latest news and discoveries from Diamond, including a special insight into how Diamond is helping the life sciences. In the meantime, if you have any questions about Diamond or the research taking place there, the email address is podcast@diamond.ac.uk. Thank you to Trevor Raymond, John Bridges, Mark Hodson, and the team at Diamond Light Source. Production this month was by Chris Smith of thenakedscientist.com. I'm Mira Senthilingam. Thanks for listening, and goodbye.
The Diamond Podcast is brought to you by Diamond Light Source and produced by thenakedscientists.com. There's more information on our website at diamond.ac.uk/podcast.